For hundreds of thousands of years, every human on Earth had dark skin, an adaptation forged under the fierce African sun. Yet somewhere along our journey, something changed. Pale skin, a trait once unknown to our species, began to spread across Europe and Asia. When did this transformation happen? Why did it occur in some populations and not others? The answers are hidden in a 50,000-year saga of migration, ice ages, shifting diets, and tiny genetic mutations. A story that rewrites everything we thought we knew about our past. The first chapter of this story begins not in Europe or Asia, but in the relentless heat of East Africa between 200,000 and 300,000 years ago, when our species, Homo sapiens, first emerged. The equatorial sun of this region is unforgiving, blasting the land with some of the highest levels of ultraviolet radiation, UVR, found anywhere on Earth. For early humans, UV exposure was both a blessing and a curse. On one hand, sunlight triggers the skin to produce vitamin D, essential for strong bones, healthy immune systems, and proper brain function. On the other, too much UVR destroys folate, a vitamin critical for fetal development, and can mutate skin cells into cancer. In this delicate balance, evolution found its solution in melanin, the pigment that colors our skin, hair, and eyes. Early Homo sapiens carried high concentrations of eumelanin, a dark, brown to black pigment that acts as a natural UV shield, absorbing and scattering harmful rays before they can damage DNA. This wasn't just a cosmetic trait, it was a survival adaptation fine-tuned over millions of years from earlier human ancestors like Homo erectus, who likely also had dark skin. For hundreds of millennia, this deep pigmentation was universal across our species because in the African tropics, light skin wasn't merely disadvantageous, it could be deadly. But our ancestors were not static. Humans are explorers by nature, and around 60,000 years ago, during a period when ice sheets locked up much of the planet's water and sea levels were lower, small groups began venturing out of Africa in a migration that would forever change our species. Following shorelines and river valleys, they moved into the Arabian Peninsula, then fanned out across southern Asia, hugging coasts where fish and shellfish provided abundant nutrition, including vitamin D. This was crucial because their diets were rich in this nutrient. There was no strong evolutionary pressure to lose the protective shield of dark skin, even as they left the equator behind. Over tens of thousands of years, these early migrants reached Southeast Asia, Melanesia, and Australia. Populations like the modern-day Andaman Islanders and Aboriginal Australians still bear the genetic and phenotypic legacy of those first journeys, with skin adapted to block intense sunlight in tropical and subtropical zones. The game began to change when humans pushed into higher latitudes, regions where the sun's angle is lower, its rays weaker, and winters long and dim. Here, ultraviolet B radiation, UVB, the type needed to trigger vitamin D production in the skin, is scarce. In such places, having too much melanin could become a disadvantage because it blocks the already limited UVB from penetrating the skin. Over time, this could lead to chronic vitamin D deficiency, causing rickets, brittle bones, and compromised immunity, potentially fatal in prehistoric life. The farther north humans traveled, the stronger this selective pressure became. Yet even with this environmental push, genetic change moves slowly. By the time modern humans entered Europe in large numbers, around 45,000 years ago, they were still dark-skinned. These were the people of the Aurignacian culture, skilled hunter-gatherers whose stone blades, bone tools, and symbolic art hint at a complex, adaptable society. Popular imagination, especially in the 19th century, often painted these early Europeans as pale-skinned proto-whites, but this was a projection based on the artist's own appearances, not on evidence. In reality, their skin would have been shades of brown, adapted to their African heritage. And for many of them, the environment didn't force a change. Diets heavy in fatty fish, seals, and large game provided ample vitamin D, bypassing the need for lighter skin. This is why, even today, indigenous Arctic peoples such as the Inuit can have darker skin despite living in regions with very low sunlight. Their diet makes up the difference. It's important to understand that skin color is only one of many traits shaped by the environment, and its evolution depends on a complex interplay of factors. In Ice Age Europe, UV levels were low, but cultural and dietary practices buffered the effects. Early Europeans lived in small, scattered groups, often isolated by vast stretches of forest, tundra, or ice. Genetic drift, the random fluctuation of traits in small populations, may have influenced their appearance as much as natural selection. Some areas might have seen gradual shifts toward lighter skin if diets lacked vitamin D-rich foods, while others maintained darker pigmentation for millennia. The archaeological record and genetic evidence suggest that for tens of thousands of years after leaving Africa, humans across Eurasia retained a variety of skin tones with no continent-wide push toward paleness. This challenges the simplistic idea that moving north automatically turns populations lighter over a few generations. In reality, the change is slow, uneven, and heavily dependent on local conditions. If you could step into a time machine and visit Ice Age Europe, you would find a continent inhabited by people whose skin ranged from deep brown to medium tones, their bodies wrapped in animal hides, their hands carving reindeer antler into tools, and their minds creating symbolic art on cave walls. They were the descendants of Africans, still carrying the pigment of their birthplace, and the evolutionary clock toward white skin had only just begun to tick. The transformation from universally dark-skinned ancestors to the wide range of lighter skin tones found in much of Europe today was neither sudden nor uniform. It was a slow, tangled evolutionary story that unfolded over tens of thousands of years. This change was not the work of one single moment in history, nor the result of one light-skinned gene suddenly sweeping across the continent. Instead, it was a long-term interplay between biology, climate, migration, and chance, with small but powerful genetic changes building up over countless generations. To understand this transformation, we first need to step into the microscopic world of human skin, where two main pigments control our color: eumelanin, a dark brown to black pigment that acts like a natural sunscreen, protecting us from ultraviolet (UV) damage, and pheomelanin, a yellow to reddish pigment that offers far less UV protection but gives hair and skin a lighter hue. Every human has both, but the exact balance between them is determined by specific genes. And in the European story, 3 genes dominate the narrative: SLC24A5, SLC45A2, and TYRP1. Variations in these genes, known as mutations, shift the ratio toward lower eumelanin and higher pheomelanin, letting more UVB radiation penetrate the skin. In high-latitude environments with long winters and weak sunlight, this was a survival advantage because UVB triggers the production of vitamin D, essential for bone health, immune function, and reproduction. But these mutations were not born in the same place or time, and they did not spread evenly across the map. Some likely arose in far northern Eurasia during the Ice Age, where the low light levels exerted intense evolutionary pressure for skin that could absorb as much sunlight as possible. Others may have originated further south and spread northward through waves of migration. Ancient DNA has revealed just how staggered this process was. For much of the 20th century, scientists assumed that light skin, light hair, and light eyes evolved together as a package deal in Europe. The genetic record has now shattered that idea. Different traits appeared at different times, often in different populations. A famous example comes from the remains of a 7,000-year-old hunter-gatherer from Logroño, Spain. His genome shows that he had the mutation for blue eyes, controlled by the OCA2/HERC2 gene complex, yet his skin was still dark brown, closely resembling that of early African humans. This means the blue eye mutation became widespread in Europe thousands of years before the most common light skin mutations did. In contrast, a 7,700-year-old skeleton from Motala in southern Sweden paints a completely different picture. This individual carried both of the major European light skin gene variants, SLC24A5 and SLC45A2, along with the mutations for blonde hair and blue eyes. Here, the package was already assembled long before it became common further south. These stark differences between two populations living in the same general era show that Europe was not a single synchronized evolutionary stage, but a patchwork of genetic and physical diversity. Geography, climate, and diet were the main forces shaping this variation. In the sunny Mediterranean, darker skin lingered far longer because vitamin D was still easily produced from year-round sunlight, and diets rich in fish, dairy, and animal fat provided extra vitamin D from food. In Northern Europe, however, where winters could last half the year and the sun stayed low even in summer, lighter skin was strongly favored by natural selection, allowing populations to make the most of every ray of weak sunlight. When farming arrived in Europe around 8,000 years ago, carried by migrants from the Near East, the genetic landscape became even more complex. These early farmers brought with them new light skin alleles which mixed with the genes of local hunter-gatherers. The result was a continent where skin tones, hair colors, and eye colors varied wildly from region to region, sometimes even between neighboring valleys. Archaeogenetic studies suggest that during this period, you could travel a few days' walk and encounter one community with pale skin, blonde hair, and blue eyes, and another with deep brown skin and dark hair, yet both groups might share similar tools, pottery styles, and trading networks. This shows that physical appearance in prehistoric Europe was not a marker of separate races, but a reflection of different evolutionary pressures acting on interconnected populations. By the Bronze Age, around 4,000 years ago, the spread of steppe herders from the Eurasian grasslands introduced yet more genetic diversity, including additional light-skinned variants, into Europe's population. But even then, the process was incomplete. Pockets of darker-skinned communities still existed alongside lighter-skinned ones, proving that this was not a rapid total replacement, but a gradual, overlapping shift. The modern European look, pale skin paired with light or medium hair and a range of eye colors, is therefore not an ancient, unchanging identity, but a relatively recent outcome of climatic adaptation, migration, and genetic blending. It's the product of a long, messy history in which survival, not beauty or culture, dictated which traits spread. The ancient DNA record makes one thing clear: the faces of prehistoric Europe would have looked far more varied than the stereotypes we imagine today, and the genes behind those faces tell a story not of separation, but of shared ancestry shaped by the slow hand of evolution. By the final millennia before recorded history, the gradual, uneven evolution of European skin color was pushed into its most transformative and accelerated phase, a period where multiple forces, climate, diet, migration, and genetic drift converged to produce the complexion patterns familiar today, though they were far from universal and still in flux. Between roughly 5,000 and 3,000 years ago, massive population movements reshaped the genetic structure of Europe, most notably with the expansion of the Yamnaya and related pastoralist cultures from the Pontic-Caspian steppe. These were mobile, horse-riding herders with advanced metal tools, complex social hierarchies, and a subsistence strategy that combined herding, dairy production, and seasonal agriculture. Their migration was not a single wave, but a centuries-long process that carried them deep into Central and Western Europe, where they intermarried with established Neolithic farming communities, descendants of earlier migrants from the Near East, and with the scattered Mesolithic hunter-gatherer remnants of the far north. Crucially, the Yamnaya and similar steppe groups carried high frequencies of SLC24A5 and SLC45A2, two of the most important alleles for light skin in modern Europeans, as well as possible modifier genes that subtly reduced melanin synthesis and altered the skin's ability to handle UV radiation. When these alleles mixed with local populations, their frequency rose sharply, especially in northern regions where long winters and weak sunlight created an intense need for efficient vitamin D production through UVB absorption. This biological pressure was further magnified by the dietary shift that accompanied the agricultural revolution, Whereas Mesolithic hunter-gatherers obtained vitamin D through fish, wild game, and varied plant sources, farming societies relied heavily on grains, with far less vitamin D content making lighter skin a selective advantage in preventing rickets and improving fertility. In the sunnier south, environmental selection for paler skin was weaker, and darker pigmentation still conferred UV protection, but the constant churn of human mobility, maritime trade across the Mediterranean, seasonal migrations, war captives, and intermarriage through alliances ensured that the same light skin alleles spread widely even where they were less advantageous. By the Iron Age, around 2,500 years ago, the genetic landscape of Europe had become a complex mosaic. In the north, very light complexions were now common. In the Mediterranean basin, skin tones ranged from pale to deep olive, reflecting both adaptation and centuries of mixing. And in between lay a spectrum shaped by local climate, diet, and ancestry. This was also an age of enormous connectivity. Celtic migrations radiated through Western Europe. Greek colonists established city-states from Spain to the Black Sea. Phoenician traders linked North Africa to Iberia, and the movement of goods inevitably meant the movement of people and genes. Yet even as pale skin became dominant in much of the north, genetic diversity persisted. Alleles for darker pigmentation remained embedded in the population, able to resurface in individuals when inherited in certain combinations. Environmental conditions continued to fluctuate, and events like the medieval warm period and the Little Ice Age in later centuries subtly shifted selection pressures again, showing that pigmentation evolution is never truly finished. Modern DNA studies confirm this late emergence. The dominance of the key light skin alleles in Europe is less than 5,000 years old, astonishingly recent in evolutionary terms. And Europe's pale complexion is not a timeless default, but a fragile adaptation born from a collision of migrations, farming, and survival strategies, a temporary outcome in a story that has been in motion for hundreds of thousands of years and is still quietly changing today. As Europe entered the historical era, the biological journey of skin color entered a new and paradoxical stage, one where the same forces that had once driven the rapid rise of pale skin began to be disrupted, reversed, and redefined by technology, culture, and global connectivity. The Roman Empire, with its vast trade networks stretching from Britain to North Africa and from Iberia to the Middle East, acted as a genetic blender, moving soldiers, merchants, slaves, and settlers across thousands of kilometers, introducing new pigmentation genes into every province. After Rome's fall, the so-called Dark Ages were anything but genetically stagnant. Viking raiders from Scandinavia, Arab and Berber expansion into Iberia, Slavic migrations, and the Byzantine Empire's multicultural networks all brought waves of genetic diversity. But the biggest shift was yet to come: the age of exploration and the rise of global empires in the last 500 years. The transatlantic slave trade, colonial migrations, and the Industrial Revolution's mass urbanization erased the isolation that had once allowed regional pigmentation patterns to remain distinct. At the same time, technological advancements, from glass windows to vitamin supplements, reduced the evolutionary pressure for lighter skin in low UV regions, while modern travel and intermarriage have mixed ancestries in ways unprecedented in human history. Today, pale skin is no longer purely a survival adaptation in Europe, but a legacy of a very recent evolutionary bottleneck, existing in a global context where climate adaptation is increasingly overridden by cultural preference, migration, and medicine. Yet genetics still whispers the story. Alleles like SLC24A5 and SLC45A2 remain widespread in Europe, but their dominance is diluted in cosmopolitan cities, where children are born with a kaleidoscope of skin tones reflecting thousands of years of human movement. Ironically, the same modern world that makes skin color less biologically relevant also makes it more socially visible. From fashion industries valorizing tanning or pale aesthetics to political debates on immigration and identity. In the end, Europe's light skin is not a timeless emblem of its people, but a temporary adaptation forged in the crucible of Ice Age UV scarcity, accelerated by steppe migrations and farming diets, and now carried forward in an age where evolution has slowed, but history never stops. The future of skin color will not be shaped by the slow hand of natural selection alone, but by the fast, chaotic forces of culture, migration, and global exchange. And that future, like the past, will be far more complex than any simple map of light and dark.